Hi, I will present our work of a two-step approach for implicit event argument detection. So for this task, we are aiming to do event argument detection that can go beyond sentence boundaries. This is usually called non-local or implicit arguments. For example, in these sentences, you can see that there are two sentences, and for the purchase event that we are interested in, it is triggered by the word bought, which it appears as the second sentence. And we want to extract the money argument, which actually appears at the first sentence. So this requires that our argument detector should go across sentences. This is actually very similar to semantic row labeling problems, but just with more candidates. For semantic row labeling, we usually have two kinds of methods. The more recent one is span-based extraction, which directly extracts the argument spans. But it might not be quite efficient because the candidate is quadratic to the input length. And traditionally, we have the BIO-style sequence labeling method. It can run in linear time, but it's not quite flexible to deal with some complex cases like nested mentions. So here in this work, we utilize a two-step approach. In the first step, we only detect the head words of the argument. And in a second step, we further expand the head words of the argument to their word spans. So here is the basic architecture of our model. So at the basic, we have the BERT encoder, which produces the contextualized representations of tokens. And in the first step, we have a bi-affine row scaler to select the head word of arguments. And with this, in a second step, we have the head-to-span expander that can expand from the head word to the whole span. It is actually two simple classifiers to select left and right boundaries. So in our experiments, we are using the RAMS dataset, which is a recent large-scale event dataset that can include implicit arguments. We are focusing on argument detection, and we assume that we are giving event triggers. We focus on two settings. The first one is following the original RAMS paper, in that we assume that we are giving gold spans. And the second setting is our main setting, that is, we are doing foot detection from the raw inputs. Since the RAMS dataset does not annotate head words, we automatically obtain them using a Stanford parser. We simply utilize the dependency tree and use a simple heuristic to detect head words. In the first setting that assumes the gold spans, we're comparing with the span-based model from the RAMS paper. So here we are comparing with the first line to the third line and second line to the fourth line, because they are in different settings. And we can, if we look at F1 scores, we can see that basically they're very similar to each other. This shows that the head words, the representations of the head words already contain enough information for the whole span, which supports our method. And in the second setting, we're doing full argument detection. In this setting, we're comparing with the sequence labeling model. And you can see that the results are average over 5 rounds. You can see that all methods averagely get better results. And actually, the difference is not too much. And we think that it's mainly due to the powerfulness of BERT encoder, because both this model are utilize the same encoder, only the decoder is different. And finally, we further have some analysis on the fall detection experiments. For full analysis, please refer to our paper. Here we only show two interesting cases. The first one is the analysis breakdown on rows and local percentage. So here by local percentage, we mean that what percentage of the argument mentions appear in the same sentence of the event trigger. So we can see that basically the F1 scores is correlated with the local percentage. So when the arguments are more non-local, you can see that they get lower F1 scores. And actually, if you look at the rows, they are usually non-core rows. And for the local arguments, we can see that they usually get higher F1 scores, and they are usually core rows of the event frames. In our second analysis, we're doing a manual analysis on the 200 samples of the event frames. We classify each argument arrow into some categories. So here we have span arrow, which means that we detect the correct head word, but we expand to the wrong span. We also have coreference side arrows, which means that we extract a coreference of the gold annotated argument mentioned. We also have annotation problems, some partial problems of frame arrows. And lastly, you can see that there is a large group of other arrows. Those are the ones that we cannot find very interesting patterns, and many of them are over-predicting or missing of the arguments. So finally, come to the conclusion, we can see that implicit argumentation is still a very difficult problem. It requires actual multi-sentence semantic understanding, and especially the results are still very low on implicit and non-core arguments. So this calls for more future work on this line. We hope that our work analysis can shed some light on this line of research. Thanks a lot.